Okay, today's starter involves both electric fields and electric potential. So we're just going to have some generic object that's got a mass of 0.5 kilograms and it carries a net charge of 25 microcoulombs, micro times 10 to the negative 6. The object accelerates from rest to a speed of 20 meters per second in 0.5 seconds due to a uniform electric field. A, what is the electric field? B, how far did the object move? And C, what was the change in electric potential for the object? So let's set that up with given, find, and solve. Let me zoom out a little bit, make room on the screen. So given, we've got just some object, and it's got a charge on it of 25 microcoulombs. So we'll put little pluses on there. But it does have a mass of 0.500 kilograms. So this could just be some object with a static electric charge on it. And it accelerates from rest, so its initial velocity is 0. Its final velocity is 20 meters per second, and that happens at t equals 0.5 seconds. And we want to find, well, for part A, what is the electric field? And then B, how far did the object move? We'll call that delta x. And then C, what was the change in potential for the object? Okay? And then let's solve it. Now for part A, we want the electric field. Now, the electric field, by definition, is the electric force divided by the charge on the object. So, do we know what the charge on the object is? Yes, that's given. Do we know what the force is? No, we have to find it based on what's given. So, if I draw a little, almost like a free body diagram, here's my object, and I'm just going to say, let's ignore gravity. Maybe this is like a little car on wheels. We put an electric field, and so the normal force and gravity cancel out and all that. But we're just going to say that this is the electric force, and that's going to be equal to mass times acceleration. So what's the acceleration? Well, we know what the change in velocity is, and we know what the change in time is. So the acceleration equals change in velocity over change in time. Or you could use the first kinematic equation. V equals V naught plus AT, and then solve for A. You basically get this. So the change in velocity, well, it's going 20 meters per second. Subtract the initial velocity, but it started from rest. And then this all happened in 0.5 seconds. So 20 divided by 0.5, what is that? 40 meters per second squared. That's my acceleration. So now I can find my electric force. Well, let's just solve for E now. E is equal to the electric force, which is the mass, 0.5 kilograms, times the acceleration, 40 meters per second squared. And a kilogram meter per second squared is a Newton. Okay, so we're good. And then we're going to divide that by 25 microcoulombs. And so I'm going to do the math here, 0.5 times 40. And then I'm going to divide that by 25 times 10 to the negative 6. We get a big number, 800,000. Newtons per coulomb. Or better yet, you could say that this is 8.00 times 10 to the what? 5? Newtons per coulomb. Either answer would work. And notice I'm trying to do these problems kind of like what they'll do on the AP test, where you don't really need a lot of calculation, or you don't need your calculator that much, but we'll see. And then part B, Let's do part B down here. Let's see, we want to know how far the object moves. So that's delta x. So what do we know kinematically? We know the initial velocity, the final velocity, and time, and I'm trying to find delta x. I don't know the I do know the acceleration, but what equation doesn't have acceleration in it? I mean, what if I made a mistake doing that? So I'm going to use the second kinematic equation. Remember those from way back? This is going to be v plus v naught divided by 2. This gives me the average velocity times time. And so delta x, this is going to be 20 meters per second plus 0 divided by 2, and then times 0.5 seconds. And so delta x is equal to, well, I don't need a calculator, right? Because what is 20 divided by 2 is 10. 10 times 0.5 is 5. 5 meters. Nice and easy. Now, let's figure out what the change in voltage is. This object, if I imagine this object in space, and I'm going to do it up here because I've got lots of room up here. Let's do part C up here. So I've got this uniform electric field, right? And I know what that field is now. And the object started from rest, and I'll just draw the object with positive charge on it right here. Do you see that it's moving this way, right? It moved that way 5 meters. Okay, listen, because we haven't had a lot of practice and a lot of time for this, and because we are kind of running out of time. When an object falls, think of it as falling down an electric field. It loses gravitational potential energy. Electric potential energy. Right? I mean, this pencil, when it falls down, it loses gravitational potential. Now, this object right here, somebody had to put it there. Somebody had to do work to get this charged object work against the electric field, so it's got potential. Then when you release it, it gives up that potential. And so the equation is the change in voltage is equal to negative E times delta x times the cosine of the angle between them. Of course, here it's going to move to the right. The electric field is to the right, so the angle between this vector and this vector is 0. What's the cosine of 0? 1. And if I'm going to do it like this, I shouldn't put these vector hats on. It's just E times delta times. And so, oh, and this shouldn't be V. Sorry. What should this be? Capital V, like that. What is, look, usually this means speed or velocity. So, I mean, it's not wrong if you do that. It's just annoying. All right. So, negative, and then do we know what the magnitude? Yes, it's 8.00 times 10 to the 5 newtons per coulomb. Multiply that by 5 meters. So what's the change in voltage? Well, that's 8 times 5 is 40. And then 40 times 10 to the negative, or 10 to the 5, that would be 4 times 10 to the 6. Volts. Now look, what's a newton times a meter? A newton times a meter is a joule, and a joule of energy per coulomb of charge that it carries is volts. So we lost 4 million volts in doing this. Now actually, these kinds of really super high voltages are pretty common in static electricity problems. If they have a field this strong, you're going to have a drop in, and this is how much potential energy per unit charge it lost. Okay, where did it go? Where did that energy go? By the way, in fact, I could have put a part D and a part E and a part F on this. Maybe they'll do that on the AP test, but where did that energy go? Well, what is the object doing right here? It's moving. It's got kinetic energy. So one of the things you could do, just to practice with this, figure out how much kinetic energy it gained, multiply the change in voltage by the charge on the object. That'll give you the electric potential energy lost. The electric potential energy lost should be equal to the kinetic energy gained. So, anyway, but this is enough for right now. So there's a little bit of everything from first semester and second semester. Look, we drew a little free body diagram, use kinematics to get, use kinematics, and then as well as, electricity and fields and potential. So these are the kind of things they're going to want you to do. Some of it's going to be all mixed up. Does this make sense to everybody? Can you do a problem like this on the test? Maybe. We're going to find out. All right. So, if there are no questions, that is